Okay, yeah. Good morning, everybody. Thank you for having me here. Um, I'm very excited and learned a lot from yesterday's wonderful talks. So today I'm going to talk about spatial intelligence, which is a fancy name. Um, actually, my work is still mostly 3D vision, 3D reconstruction, generation, and motion control, but I just follow the trend, call it spatial intelligence. When I joined Alibaba in 2019, they asked me to find a name for my own group at that time. And we discussed a lot, and eventually we choose the name Spatial Computing at the 2019. At that time, nobody know what it is. But all in sudden, after Fei Fei talked about the spatial intelligence, everybody is talking about spatial intelligence. So in today's talk, I'm going to introduce some of our most recent works in 3D reconstruction and generation and robot motion control. It looks like a collection of some uncorrelated works, but I put it in this way because I hope to have more interaction and more discussions with you. So I try to cover most of the different aspects of my group's work. And by the way, most of the works I'm going to talk about today are unpublished, so which means it has not been reviewed. They might contain errors, so criticisms are very welcomed. Hopefully, they will help us to improve our work. Okay? Yeah, without further ado, let's go. So, yeah, it's spatial intelligence. I don't think I need to introduce these slides for you. Basically, I think it's a different dimension of artificial intelligence. It's kind of orthogonal to the language intelligence. So, in our approach, we study spatial intelligence from three different aspects: 3D reconstruction, 3D generation, and motion control. In terms of perception, we have a number of classical problems in 3D vision, like mapping, building an environment map for the environment, and localizing your sensor or your robot, and then semantic understanding of localizing all the other objects, and then generating navigation and manipulation plans in the environment. So those are the problems we care about for 3D perception. And a very classic problem in 3D perception is the so-called structure from motion, which basically take a set of 2D images as input and then generate a 3D point cloud representation of the scene and getting the camera poses as well. But the traditional methods in structure from motion has many limitations. For example, when the viewpoint change is large, it's very hard to coordinate the different images, and when there's insufficient texture information, it is also very hard to solve the relative motion between the images. So traditional methods actually face a lot of challenges in this classic problem. The most recent advance is this so-called VGGT, which won the Best Paper Award at CVPR this year. And actually, it begins from DUST3R, which was a CVPR paper last year, 2024. Personally, I think that is the first deep learning-based structure from motion work that can firstly obtain high-quality results, and number two, discard all so-called inductive bias or human knowledges. Before that, then a few other works like Demon or BA-LET or CodeSlam, but most of these deep learning-based structure from motion methods, either they generate poor results or they're still mostly based on boundary adjustment and so on. But I think DUST3R is really the first one that completely discard all those human knowledges and just use end-to-end learning to learn this kind of capability from data. So VGGT is a scale up of DUST3R. It basically directly regress the 3D camera poses and the 3D scene points from just the images, and it is trained on huge amounts of input data, and it works really well, and sometimes even outperforms the traditional algorithms. But it has a limitation that it cannot scale up. Usually, while it's mainly limited by the GPU memory. It's like if you throw like 1,000 images to your GPU, then you cannot hold all those images in your GPU. So it's a problem we need to fix. And to address this problem, we actually very much inspired by the traditional wisdom. Thinking about, if you want to build a large-scale structure from motion system, or typically like a visual SNAM system, we want to treat all the input frames in the same way. Like in a typical visual SNAM system, there are so-called keyframes. Mapping is only performed on the keyframes, and for the non-keyframes, you just do localization. So basically, we are doing something very similar here. Instead of throw all the images to feed them all to the GPU memory, we first pick a subset of the so-called anchor images, which should try to cover the entire thing, and they are the anchors, and such that we can perform the mapping just with those anchor images and get a 3D scene representation. And once we can generate a 3D scene representation from those anchor images, we can then just perform localization on all the other images. In that way, it can help the system to scale up very easily to more than like 10,000 images and maybe even more. So this is a very simple idea, but I really like this idea. It kind of tells me that human knowledge is still relevant in 3D vision. We can still use our knowledge to improve the system performance. And this is a short video example. So the input is this video on the upper left corner, and showing in the middle is our 3D reconstruction. We're comparing with some relevant works, and basically we can find, like for example, this Cut3R. You can see its 3D reconstruction is mostly distorted, and we get a better 3D quality. And yeah, I think there's another comparison. This VGGT, you can see the ghost effects, which is generated, due to the maybe inaccurate motion of the cameras, while our method can generate a much better results on this challenging example. Yeah. This is another example, and we have the input video, and then we have the camera poses and the 3D point clouds. And comparing with other alternative approaches, we get a better, 3D quality. Yeah. So that is the 3D reconstruction work. We tested on more examples, and we also reported some quantitative results. But briefly speaking, I think our method generates better reconstruction quality, and it runs very quickly. The computational efficiency is very much similar to those SNAM systems like the Droid SNAM. If you look at the table on the right, our method takes on average like 3 minutes to process those sequences, and the Droid SNAM takes also about 3 minutes. So it's really efficient, like real-time visual SNAM systems. And all those experiments are performed on a single GPU, so it's quite efficient. And in the next I'd like to introduce this spatial LM work, which is, basically after you get the point clouds from structure from motion, we can apply maybe a language model to, it's actually a visual language model to detect the objects from the scene, like this. Basically, at that time, we actually used the master 3R, but we can also collect the method we just introduced, the cell recon, to feed the 3D point clouds into this model to generate object detections. So these are the detection results. We can get this kind of 3D semantic maps for maybe robotics applications or maybe AR applications as well. Yeah. Yeah, exactly. Actually, it's a collaborated work with Qunhe. The researcher there is actually Professor Yima's former PhD student, Zhou Zihan. They are actually having, they have a lot of data. This is, to me, the most exciting part of this collaboration. So we published this spatial gen or spatial LM data set with a lot of 3D indoor data. Actually, before this data set, perhaps the largest indoor data set contains only like a few hundred or maybe at most 1,000 3D rooms with object annotations and 3D ground truths. But in this work, we published 57K rooms with all kinds of annotations, including depth images and object segmentation, 3D bounding boxes, and so on. So I think this data set could be very useful. And the first work, spatial LM, has just been accepted at a new RIPS, and the spatial gen is still under review at this stage. Yeah. And after that, I'd like to talk a little bit about 3D generation, which I think is, we try to develop those generation models in the future to make it like a kind of foundation model. Hope it will help us to solve the maybe 3D reconstruction and 3D perception problems in a better way. But at this stage, we are still at the stage of developing object and the scene generation models. So this is an object generation model published this year at the CVPR. Mostly in this work, we take two different stages to generate a 3D model from coarse to fine. It's pretty much the same pipeline as developed by Professor Gao Hua here. He's not here today. Yeah. Oh, yeah, there. His Mecanangino, I think, is the first work on 3D native diffusion and 3D generation. So we pretty much followed that process. And I think more detail I'd like to share on this approach is really on this VAE, which is also published at this CVPR. So typically, we need to learn a VAE space, a latent space for the 3D diffusion. And we find actually there's a little technical detail that is interesting to share. Essentially, we need to, given a 3D model, we need to sample a point clouds on the surface of the 3D model and use those sampled point clouds to learn the latent space. And it turns out that if you use uniform sampling, you might not get all the shape details because, for some of the high frequency shapes, like the keyboard in this case, it will take a lot of sample points to cover all those details. And if you just take a naive uniform sampling, most likely you won't get them because you won't be able to include infinitely many sample points. So basically, we did an importance sampling and trained the VAE, trained the latent space with this kind of importance sampling, and we can get a better, VAE. Pardon? Oh, yeah. Actually, I think his talk yesterday is very inspiring. We are actually thinking along the similar direction about the combination of reconstruction and generation, or discrimination and generation in 3D. But I think in the 2D, in image space, it is much better studied because yeah, the Ladino and in 3D vision, there's no much learning-based 3D reconstruction work until the most recent Dust 3R and VGGT. Actually, there's some works that are trying to use the VGGT feature to guide the diffusion process in 3D object generation. But so far, this two feature space hasn't been unified together. They use Dino to extract the image features, but then they will upgrade it into the 3D space and so on. Yeah. Yeah. No. Yeah. And most of the 3D generation works are only for single object, while VGGT is for entire scene. Objects are not segmented or separated, so there's still a very large gap. I think we still have a long way to go in the 3D vision field. Yeah. So this is a website our students build, and that basically, if you are interested, you can visit this traverse.ai, and if you can upload a single image, it will generate a high quality 3D model and then generate the texture maps and so on in maybe 1 or 2 minutes. Yeah, this is the texture map, the model. Yeah, so after having this object generation model, we are trying to generate 3D scenes. Essentially, we hope to have like upgrading these 3D generative models to generate scenes. But so far, all the 3D scene generation works are still generating the scene object by object. Essentially, it is still an object generation model. We still don't know how to generate an entire scene in a single step. But in this approach, it is also under review now. In this approach, basically we apply some object detection and segmentation works to segment out each individual object, and then try to generate a complete image for that particular object. We call it a de-occlusion. And once we get a de-occluded image, we call the object generation module to generate a 3D object. And then we perform a pose estimation to insert those objects back into the 3D scene. So that is the basic pipeline. And what I want to emphasize here is really the de-occlusion part. We find this intermediate step is actually very helpful. Before our work, there are a few other works that take a similar approach to generate the scenes object by object, but they typically don't have this de-occlusion. What they do is that they just take maybe the occluded object image, and from those occluded image, they train a 3D object generation model directly. And it turns out that we find that the system would perform much better if you can firstly generate a complete image of the object. In that step, we can make use of those image generation models to complete the image, and then apply the 3D generation directly. I think the reason is that the 3D generation component has much less training data, usually at the scale of like a few million 3D models. But the image generation model are trained on a much larger scale of data. So it is helpful to make use of those models trained with much more data. So after the de-occlusion, we can get an 3D object generated, and then what we need to do is to solve a pose estimation. So for the pose estimation, we firstly estimate a depth map of the input image, and then we designed a few different modules, like a global module that will try to fit all the objects into the single input image with all the 3D points and the input image, and a local module that will just consider an individual object. We have this local module because it can make the orientation estimation more accurate, because mostly the orientation can be determined from that single object, but the scale and the translation needs to refer to the global context and so on. So here are a bit more details. So for each object, we have its 3D token, and then we insert 3 additional tokens for rotation, translation, and scale or size estimation. And then we apply this attention mechanisms to eventually compute all those parameters we care about. And we evaluate the system on 2 different data sets, 3D front, which is open data set of indoor things, and we also collected our own data set. We call it open set, which contains both indoor and outdoor things. And for most of the metrics, we get better results. Yeah. So here is a demo my students built based on this kind of technique. So suppose you want to generate a 3D scene for various applications. What you can do is that you can, just take a text and then run an image generation model to generate a panorama, and then you can detect and segment out each individual object and upgrade them into 3D, and then estimate the pose and the size and everything, and then put them back. Then you will be able to get a 3D scene in that way. The good part of this kind of 3D scene is that every individual object is separated. They can be sort of manipulated. We don't have like soft objects right now in the system, but it can support rigid manipulations like translations and rotations and so on. So you can imagine we can take this approach to generate like hundreds of thousands of different rooms of all kinds of environments, like apartments, factories, hospitals, and we can potentially use this kind of data as the training environment for robot applications, for humanoid robots applications, and so on. So that will make robot learning more convenient, or even testing. Otherwise, like if you want to test your humanoid robot in a hospital, you have to really send them to the real hospitals, and it could be difficult to arrange, and you won't be able to test them in so many different environments. So this kind of 3D scene generation could be very important for robotics applications. Okay, so finally, I'd like to talk a little bit about motion control. Once you have the 3D virtual environment, perhaps we can train, motion policies to control your robot. In this particular case, we control a humanoid robot to learn basketball skills. And briefly, we firstly train a neural network, a policy network, for a set of so-called atomic skills. And this is learned from videos of human demonstrations. My student plays basketball very well, so we record his motion, and use some computer vision algorithm to extract the skeleton motion and the movement of the ball. And then we train a policy network in a simulation by reinforcement learning. And it will learn those individual skills like dribble and layup and so on. And in this process, actually, there's, I think, important design is the contact graph. We find that it is very important to, let the network to understand the contact between the objects and the body. Like in this case, we just use a graph of 3 vertices, 1 vertex for the hands, and 1 vertex for the basketball, and another vertex for the whole body. And here, the dark edge means these 2 objects are in contact, and light edge means they are not contacted. Like shown on the left, in this moment, none of them are in contact, but on the right, the hands are holding the ball, and so the hand is contacting the ball. So with this kind of contact graph, we find that it is helpful to learn the policy network. So we basically design the reward function by combining 4 different rewards. Firstly, a body reward that will compare the skeleton pose of the observation and the robot, and then the object pose and the relative motion between the object and the body, and also the contact graph. So in that way, we can learn various different skills in simulation. And after we get the atomic skills, we also need to learn a high-level policy to switch between those skills so that the robot can automatically collect those different motions to achieve a high-level goal, like to score. And so with this technique, we find that it is pretty easy to design a high-level goal. Like in this case, if we want to train the robot to score, we just use some very simple reward function. Like I think this RTV is a reward for the velocity of the ball. The ball cannot stay still on the ground. And heading is a reward requiring the ball to be closer to this yellow circle. And bonus is that if you get the ball in, you get some extra bonus. And throwing, I think, is constraining the height of the ball. I forgot the details. But anyway, we can train this kind of robot to play the ball automatically. You give it a ball, and it will run to the ball automatically, and when the distance is appropriate, it will try to score it by itself. And later we further have another work to improve the data efficiency. To basically, it's a kind of like a data augmentation, because during the training data collection, you cannot collect infinitely many training samples. So we design some interpolation skills to generate more data, and then also try to make the system more robust to disturbance and so on. So that's what we did at this SIGGRAPH paper. We also try to generalize it to more general skills other than just the basketball. It can also be applied to household tasks. So my students are right now trying to make this method work on real robots. So I think, on the left, it's just for fun. It's a dancing example that trained the robot to dance. But on the right, I think it's it's the technique we are focusing. We're actually trying to get a switch between two arbitrary scales. So once it can switch between scales robustly, we then will be able to apply what we have talked about to let it play basketball. We already had some quite exciting examples. I didn't include them in the PowerPoint. It can do jump shoot, it can do layup, and it's quite interesting. Yeah. So so far I talked about a few recent works covering 3D reconstruction, 3D generation, and the robot motion control. And thank you very much for your attention. Yeah.
So let's thanks Professor Ping Tan for the great talk. And any questions? If no, I have.
I have two quick questions. So both are related to our recent papers. So one is about, let's continue our conversation about VAE. So last year at ECCV, we have a paper called Diffusion Transformer for layout generation without a VAE. So basically we study layout, but you will use the coordinates of a bounding box, basically three just variables without any VAE. And we were able to show that like you really can learn layout very kind of general way. So but we haven't applied to point clouds. I'm wondering, what if you just treat those point cloud individual points, just use their raw coordinates and just without any PVE, learn diffusion model?
Yeah. I suppose you are talking about the 2D layouts.
No, 3D.
Images.
Ours is like, our work is just layout for the bounding boxes 2D. But what I'm saying is like, what if you apply three point cloud in 3D?
Yeah. We actually tried that approach. But maybe not exactly what you described. We try to, like in 3D room generation, we try to first generate a 3D layout and then, maybe just put each object, within the 3D bounding box. It sounds like a simple approach, but turns out the challenge is that you don't have that 3D layout data. Like think about the data set we just published. That is so far the largest data set ever published on 3D indoor scenes. We only have like 50,000 rooms. And it's very limited. You won't be able to train a reasonable diffusion model on it. Yeah,
I see. So actually, your question is to my second. Your answer is to my second question.
Okay.
So then let's just talk about this one then first.
Yeah.
So yeah, I was referring to that. My second question was trying to build like a layout for 3D. Then based on layout, then generate images.
Yeah.
But you're talking about short of like a data. What about like you have 2D images?
Yeah.
And detect bounding boxes.
Yeah.
And then lift them to 3D and then train your.
Exactly. That's what we are doing right now.
Oh, okay.
So we firstly generate an image because image generation is very well trained. Okay. So you can generate a 2D scene image, and then we try to upgrade it into 3D. So that's what we did here. Let me go to the pipeline page. We basically detect and segment every individual object and upgrade each individual object into 3D and then do a post estimation to put them back.
I see. Okay, so very much aligned. Okay.
Exactly.
So then in the future, you do plan to submit a paper. Don't forget to put my name on your paper.
We actually tried the second one first.
Okay.
But then we don't have enough data.
Okay.
Initially, we get like about 10,000 different rooms. We tried the diffusion model. It can work on that particular kind of data, but it is hard to generalize. So we then switch to this approach of generating images first and then upgrade it into a scene.
Okay. Yeah. So now let's come back to my first question.
Yeah.
My first question I meant because we were using raw coordinates for the bounding boxes to study their layout. So now what I'm saying is like forget about layout. Yeah. So for each bounding box in 2D, we have four variables, right? Yeah. What if I use for each, let's say talk about 3D point cloud. generative models, not about bounding box at all. Then for each point cloud in 3D, it has X, Y, Z. And then can you try, let's say, put this X, Y, Z without VAE at all, just raw variables, and then put them into, let's say, diffusion transformer to build a diffusion models to represent 3D point clouds? That was my question, because we had some success to model 2D layouts using the raw coordinates only. Yeah, that's my question.
Then diffusion models like that for objects. Yeah. And you can do point clouds generation. But again, it's limited for objects so far. As far as I know, there's no good data set for scenes. And we haven't seen anything like that for 3D scene generation.
Yeah, so that's my question. So it's potentially feasible to do that. Talk offline, since like...
We are actually also trying it, but the VAE we are using is not directly from point clouds. Yeah, we are using a sort of a hierarchical VAE with voxels and 2D features and so on.
That's exactly my point, without VAE. Forget about VAE completely.
Well, you still need some latent space.
No, that's my point.
Yeah.
That's why our paper got accepted on ECCV without VAE at all.
Yeah.
We can talk offline. Yeah.
Okay.
Yeah.
Guys, get a paper accepted is not endorsement of correctness. Okay, that's just.
All my papers are not accepted so far. So
I think scientifically, really, is that so the reason that early on the image that you use VA is to get the sort of kind of very empirical, from my understanding, to empirically to get the dimension reduced so that we compress it a little bit better, easier. But what the study showed is that, in fact, conceptually, that's really not necessary. If the distribution you have in the high dimension spaces has very high good structure, low dimension spaces, it's likely you don't have that. You don't need that, and make it even easier. But maybe for the 3D data, depending on the distribution, if it's not too, how do I say, like a natural image, you are looking at a very, very diverse distribution. Maybe the structured object, the distribution is not very that highly complicated. Maybe learning directly is actually quite easy. It's not as, right, learning for natural images, right? So we'll see. But even study shows that if you have a target distribution already in the high dimension spaces, you don't need a VAE. Right, it's a structure.
It's hard to say. I mean, if you talk about the 2D images, they are kind of a regular structure. It's like a 2D matrix of numbers. But in 3D, well, you could divide it into voxels to have like a similar regular structure, but then you will have a memory issue. Most likely you want to use point clouds. But then if you do point clouds, it becomes
less
very
structured.
irregular.
It's less structured.
Less
so maybe
structured.
say if you look at the VAE, what it does is just very heuristic. It just push to a slightly lower dimension and make it more like a low mode distribution, right? Sparsified, isotropic, kind of Gaussian.
Yeah.
Sort of spread it a little bit. So basically, try to regularize the distribution a little bit. So then you actually go from there to do a diffusion denoising. So that's actually kind of to get an overall shape to have some kind of structure. You make it learning a little bit easier.
Kind of.
But it's like a pre-processing, kind of heuristic pre-processing.
Yeah.
Yeah, we actually think about doing it too. So now I think it's the reason to conditions on which you can actually remove it. It's getting a little bit clearer now, I think.
Yeah.
Right.
So one of my students is actually trying it. He is using like a voxel, but while you will discard those empty voxels, and within each voxel, you have like a low dimension latent space, and then concatenating them. This kind of space has been already used in object generation, like a trainers, and we are trying to generalize that for an entire scene generation. You know, instead of from generating object by object, we are trying to generate a scene as an entire scene directly.
Maybe Senghua want to come. Is Senghua here? Or maybe you can comment. Do you guys use some kind of VAE as well? I mean, some of the recent 3D work. We use some pre-processing, right? So it's kind of yes. I think to get some latent space, right? So it's useful, but again, in the reason why it is still needed, it's not quite clear. It's just I think it's a kind of a dimensionality reduction pre-processing step. But I think once we understand its role, maybe it really becomes not necessary.
I think overall 3D is much behind the 2D. For both the discriminative problem and the generative problems.
Or mostly because also the availability of data.
Yeah, data is a big issue.
Also, the dimension might be higher. Right?
Yeah, and also like for discriminative problem, there's no really learning-based 3D reconstruction until last year. So I think we are much behind.
Sure. Okay. Good. Thanks.
Yes.
Yeah, I have a question about this data issue. As you mentioned, the scene data compared with the object data is very few.
Yeah.
But so training on such data pipeline like your work can just work on some indoor scenes as usual, but it cannot generalize to any in the wild scenes. So you have mentioned some works at previous stage about Duster, and using something like this reconstruction-based method, we can just get some reconstruction results.
Yeah.
So can this data be used to train such scene generation model so that we can generalize more well to the data?
Yeah, it's a very good point. I think it is possible. While in the future, maybe we can apply these 3D reconstruction algorithms to maybe convert all the video into 3D data and try to learn some more generic scene generation. But I'm not really sure about it. Maybe video is another kind of representation. We don't have to do it in 3D. Yeah.
Actually, I disagree. I mean, video is it's very good enough for visualization, but definitely it's impossible for manipulation or reasoning.
Yeah.
Right?
Yeah.
And again, just as I said again, right? We do 3D reconstruction not for the sake of reconstruction,
Sure.
not to look at it, not to visualize. It's in fact for us to understand, navigate, and interact, manipulate it, right?
Sure.
That's the two purpose for 3D model,
Yeah.
right? But so far, many of the things, right? Even generating a video looks like it's actually maybe an intermediate step, but really not the final purpose.
Yeah.
And then what you guys are doing here, I think it's a right. At least the goal is absolutely the right goals, right? Thanks.
Yeah. Thank you. Yeah. That's all.
Yeah. A quick question regarding the basketball playing.
Yeah.
So you said that the contact graph is the most important factor in the pipeline.
Yes.
Could you elaborate a bit on what's the role that is actually playing in the pipeline?
Oh, okay.
What's
The contact graph, right?
Yeah.
And we find it is really helpful because if you don't have it, well, the policy might cheating. It's like, for example, when you hold a ball, if you can enforce the contact that the ball should not touch your body, then the contact graph will help you. Otherwise, it might, hold the ball in this way. Your body, your tummy would touch the ball. So in practice, we find that it really helps a lot in learning all those atomic skills.
I see.
Yeah.
It's kind of like a task decomposition.
Yeah. We don't have any theory for that. It's pretty much empiric. We just find that with this contact graph, it helps a lot. And I think that some recent works from different groups that they also use similar constraint.
Okay. Thank you.